So this is the outline of today's session. We mainly will cover three topics. The first one is designing RCT, and the second part, we're gonna learn about power calculations. And the third one is about the threats to the validity of RCTs. So first, I wanna review what Professor Rosell covered in his session on Monday. So remember, we talked about impact. So take this, introducing whatever intervention that hoping to improve students' test scores. So on the X, we have time. So you introduce the intervention at certain time, and in order to measure an impact, what we want to do is to create this counterfactual group to basically compare what happens without intervention. And then once we got that, then we compare the result we can observe from after intervention and compare with the counterfact group. So this is the impact we're talking about. And so in order to really measure the impact, what we need to do is to build an experiment. So the key feature to all experiment is to basically manipulate a cause in order to discover its effect. So this is different method from the observational studies, like sometimes if you use observational data, you first identify the effect, and then you're trying to discover the causal relationship, which is a much harder and tricky task. So the logic behind the experiment and also causal relationship is basically three principles. The first one is the cause must precede effect. And the second one is the cause must co-vary with the effect. And the third one is you must rule out the alternative causes. So randomized controlled trial actually can meet all the three principles, because when you give an experiment, when you create this treatment, then you measure the effect. So the cause came before the effect. And also it can easily measure the covariations. And the third, randomization makes it, basically rule out the alternative causes, because the only difference between the two groups, the treatment group and the control group, is your intervention. So I wanted to remind all of you that randomized control trial also is not a perfect method. We will cover the threats to RCTs today. So for example, the attrition and also spillover and imperfect compliance. So we're gonna cover the problems that you have to keep in mind when you run an experiment. So here is basically a flow chart of the different stages of program evaluation. So first, you wanted to target a problem, either it's trying to improve the vaccine rate, or you wanted to improve the students' test scores. So you wanted to make sure you're clear about what's the problem you're trying to solve, and also in theory, what kind of program can solve the problems. And most importantly, before you jump into the implementation phase, very important thing should, even before you do anything, is to build a theory of change. So we're gonna look at this closely. And then the rest, once you build your kind of design, then the implementation and the program assessment is kind of straightforward. So I'm not gonna go over the entire theory of change for today's session, but this link to the video below, you can watch this very detailed theory of change video, about 10 minutes after today's session. So what this means, theory of change, is basically you wanted to, in a designing experiment phase, you wanted to figure out what's your input, like what's your program activities. Either it's the multivitamin pills, like Professor Ruzel in Monday's session, his example, or other program you're trying to measure the impact of. And then once you put the input, and then you wanted to measure, what's the result. And then you also wanted to capture the intermediate outcomes. And ultimately, you want to measure the goal, like, the long-term change. So it's a little bit kind of hard to capture when you first hear this kind of, designing RCT and theory of change. So today, I'm going to use this example throughout today's session. This experiment is actually run by our team. The target, the problem we're trying to solve is the vision problem and how that affects students' education performance. So from previous study, we know that in rural China, 1 in 3 rural students are myopic, meaning they have poor vision. They're nearsighted. They can't see clearly. So when they sit in a classroom, so 1/3 of the students in the classroom will be like this little boy here, has to like squeeze his eyes in order to see. And most of the time, even, this cannot help. So he can't see the blackboard, which of course will affect his learning. So if we wanted to measure what's the impact of vision correction on myopic students' test score, so what kind of program we want to design. So as example, I said, so on the left is the student's vision with myopia. So nearsighted students, they can't see blackboard. And on the right is the students with normal vision. So in order to measure the impact of eyeglasses or vision correction on students' test score, we wanted to create, remember, the cultural factual group. So we want to measure this little boy. What happens if he got a pair of glasses, and compare to his outcome when he does not have a pair of glasses? Of course, we cannot observe the 2 outcomes at the same time, because either he got the eyeglasses or he doesn't. So he can't have both, right? So we have to use this randomized controlled trial, or RCT, an experiment to truly measure the causal impact of providing eyeglasses on students' test score. So again, every RCT, we can divide it into 3 phases. The first part is doing a baseline survey. So that includes you select your sample from study population, and then you randomly assign 1 group of students to receive treatment and the other group as a control. And so then you bring in your intervention, in this case, eyeglasses, to the treatment group. And the control group, of course, there's no intervention. And you wait for 1 semester or 2 for the follow-up survey, which also called endline survey. And then you compare the results. So the difference between the treatment group and the control group in the follow-up phase will be the true impact of the causal impact of eyeglasses, because again, the only difference between the 2 groups is 1 got eyeglasses and the other group had received no intervention. So in order to really capture the causal impact, 1 critical step is to randomly assign 1 group receive glasses and the other does not. So there are many ways you can do this. There are many ways you can randomly assign, including you can toss a coin, hand or tail, you roll a dice, or you do lottery, or there's many ways you can do that. But usually with a large sample, tossing coin or dices will not be the kind of scientific way to convince the reviewer and the readers. So more formal methods is actually use statistical software to do it. So before we run, we go ahead to do the assignment, we need to think about on what level you want to do the randomization. So usually when we talk about RCT design, it's either in individual level or at the group level. So this is example of individual level. So for example, we wanted to randomize, choose like some students, say in blue circles, receive glasses, and some students, for example, in red circles, they don't receive eyeglasses. So this is at the individual level. And also we can do at the group level or called cluster level. And so group level, it can go either at class level. So within the same school, you can give class A, B treatment group, and C, D, E as a control, and then the rest. So this is at class level. So one class of the students is one unit in your randomized control trial. And you can also do randomization at the school level. So I want you to pause a little bit here to think about what's the problem? Why do we care? Individual level, class level, or school level? Think about this, and when we talk about the threats to the validity of RCTs, we will go back and revisit why do we need to think about the randomization at different level. All right. So the randomization is actually pretty straightforward because we do the baseline survey, then we know the list of schools in the baseline, right? So we know the sample frame. So all we need to do is actually to use either Excel, Stata, or R to basically ask the software to randomly assign either treatment or control variable to each school in our sample frame. And also that's not done. Once you do the randomization, the most important step is actually to check the balance. So what this means is you wanted to make sure the two groups, the control group and the treatment group, are identical in a lot of variables. So how to check the balance, and this is basically how do you make sure the two groups are identical. What this means is you should want to make sure that the two groups look the same on average. So say, for example, this eyeglasses experiment, we randomized at school level. So each, all the students in one school, either all of them get eyeglasses or none of them get glasses. So then you wanted to use the data you collected from baseline. So for each baseline variable, you want to make sure that they are balanced. When you run a regression like this, the outcome variable is the baseline outcome. So for example, the test score, right? You want to make sure the treatment group and the control group have the same baseline test score. So the beta here should be not significant, right? And you want to test each of the baseline. Essentially, you wanted to make sure the key outcome variable and also the student, class, school level variables are the same. So what you wanted to include in your balance check is definitely the main outcome if it's available, and also generally some basic characteristics, for example, students' gender or the number of students in each class, or the school level, like, you know, the students teacher ratio that, you know, usually indicates the teaching quality in certain schools. So you want to make sure these kind of basic characteristics are balanced. Again, when you run a balance check, sometimes we don't get perfect results. Like if you test 20 variables, you know, by chance, there will be at least 1 or 2 variables that are not balanced, which is fine. What you can do is trying to get most of the key variables are balanced. If it's not balanced, then you can rerun the randomization and regroup them. And alternatively, instead of like testing each variable alone, you can also do this omnibus test, which is you want to run the regression with treatment as variable as the outcome, and then you put all the baseline characteristics variable in the right hand. And then after you run the regression, you want to do a F-test to make sure all the coefficients on the baseline variables are jointly not equal to 0. So, you know, instead of doing it individually, we wanted to see that the whole baseline characters at, you know, overall level are balanced. So again, like I said, if you get a big imbalance, what should you do? Always you can, you know, you can use kind of add more control variables to it, or you can just rerun them, randomize, you know, regroup them and trying to get as many variables balanced as possible. So that's the designing phase. There are, you know, things that you should keep in mind: theory of change and randomizations. The second part of today's session, I wanted to talk about the power calculation, why that's, you know, important. So before we jump deep to power calculation, I wanted to briefly kind of review the two basic kind of mathematic rules that we learned before. The first one is the law of large numbers. Basically, what this means is the more sample you take, the closer average are to the true population. So what this means, I did this like visualization for you. So imagine this is the population, right? This is the distribution of the population. This is all the students in the population of interest. Let's say this is their test score. And of course, usually the population distribution will follow a normal distribution, this nicely bell-shaped. When we say select 250 students as our sample, so the 250 students test score distribution will follow like this. It's wider, right? Because the sample size is a little bit small. As the sample increase, the sample size from 250 to 1,000, we can see that the distribution of the test score is moving more closely towards the normal the population, right? So when the sample size increased to 10,000, basically what we see here is the sample distribution kind of overlapped with the true population distribution. So this is the law of large number. So again, when you increase to 10,000 students, then you get even nicer distribution here. So the first one is the law of large numbers. And the second one I wanted to remind you is the central limit theorem. So basically what this means is the more sample you take, the more the distribution of average looks like a normal distribution. There's a slightly difference between the two. Here I did again a visualization of this. So imagine this is the population distribution. This time it's not a perfect bell-shaped normal distribution. It's the population distribution is scrolled towards the left. So the average is actually in the middle, not under the peak. So when we draw a sample of, say, 30 students, the average of our sample can still overlap with the population average, right? Because they have the same or similar average, score. And also when you draw a sample of 30 students 1,000 times, right? So again, this is not increasing the sample of students here. This is we're increasing the draw, like, we draw 30 students each time and we repeat this for 1,000 times. And then we got the distribution of the average of each draw. And again, we can see that the more sample we draw, the closer the average of the sample is, closer to the population average. So when we draw a sample of 30 students for 10,000 times, again, the average of our sample is the same as the population average. So these are the two kind of basic mathematical, laws that we learned before. So how does that relate it to the RCT we're talking about today? So when we run an experiment, we get a measure of the average of treatment score, and we also get an average measure of the control score. So how do we know that our results are true, right? How do we know that we're confident with the impact we measured? And also a related question is, how big of a sample do we need for our RCT? Of course, the larger sample size, the better, but that means the project will be more costly. So with limited research budget, we wanted to find the right sample size to run our experiment to make it more cost effective. So here again, this is going back to the two kind of distribution, which Professor Rosell covered in his session. So for example, this is the HB, the homoglobal level distribution from the control group indicated in blue and the treatment group indicated in red here. So from the distribution graph here, we can kind of see that the treatment group has a higher average by 7 points. So there is like a slightly difference between the two groups. But the question is, how confident are we with this result? In other words, is this significant? So again, we wanted to know if we run the experiment again, like remember the 30 students draw each time. What if we draw the experiment? If we run the experiment over and over again, say 1,000 times, the average would be close to what we found here or not, right? So this is what we need to test. How do we do this? It's called hypothesis testing. Before we go to the testing part, I wanted to really highlight here the null hypothesis is that there is no impact of the program on the outcome, i.e. the impact you got is the true impact is 0, right? So we always start by assuming that the program either it's eyeglasses or giving vitamin pills or vaccine does not have any impact or did not cause any change. And then we ask, so how likely is it when we find the difference, either it's 7 points in the hemoglobin test, or like, 10 points in mass test score. This beta hat we're seeing here, is this true, the true effect is actually 0 or not? So if it's very unlikely that our results are due to chance, like luck, not because the true impact of the program, then we reject the null hypothesis. So usually the 5% significant level means the probability of the result is because of luck. So if we reject the null hypothesis, this means our program had a significant impact. This is a little bit kind of, tricky to understand. Again, I use this, graph to show you. So imagine, the null hypothesis, the true effect, the distribution of the result would like this if there's no effect size is 0. So if the effect we measure from our experiment falls into this red area, i.e. it's, if there's a high likelihood it's different from 0, then we can reject the null hypothesis, meaning our experiment indeed have a significant impact. All right. So there are 2 ways that this can not be true, because the truths say it's either the program is effective or it has no impact, right? But then we use the sample we have and draw our conclusion from that. So if it's, the truth is effective and our conclusion is effective, then it's fine, it's happy face. Or if the truth is no effect and our conclusion is no effect, which is also fine. So that means we use our sample, run the experiment, and we find the truth. But then it could be messed up, because sometimes when the truth is no impact, the program did not work, and our conclusion is it works. So this type 1 error also, gives us this false positive result. Or it can be type 2 error. It means when there's the truth is effective, but our conclusion from our sample says there's no impact. This usually caused by the low power, because we don't have enough sample size to draw the right conclusion. So how does this work is the type 2 error is, we've failed to reject the null hypothesis. So the power we're talking about here is if the null hypothesis is false, then the probability that we will detect an effect. So if the power is low, it's easier to mess up and get an incorrect conclusion. Again, I use visualized graph to show you. So for example, the null hypothesis, right? The control group average, we often set it to 0, and the treatment, the impact we measured is beta here. So the difference between the control group and treatment group, we want to know how confident we are in this. So when we remember the significant level at 5% means the treatment average needs to fall into this green tail area, then we can draw the conclusion that it's significant. So the power here, it means the probability. So the kind of purple area on this graph, it shows the power, which is the probability we obtain a treatment effect, which is lead us to reject the null hypothesis. So usually we want this area to be, the probability to be larger than 80%. So the power usually we wanted to set to more than 80%. It sounds like kind of a lot of information, but just keep in mind that there are many factors that can influence power. The first one is effect size. So when your program have a big effect size, and then it's easier to detect from your sample, right? So the bigger effect size, the easier it is to distinguish from zero. And the second one is the variance, which is the variability in the outcome variable. So if the outcome variable is there's not much variance in it, then it's easier to find an effect. And of course, the sample size. A larger sample means that the treatment and the control group are more representative of the overall population and make it easier to find an impact. And also the way you split your sample. So usually when we do a randomized control trial, we split the treatment and control group into 50 and 50. So half goes to treatment group and half goes to control group. So equal proportion make it easier to distinguish an effect. And the last one we wanted to consider is clustering. So remember the randomization, we wanted to, if it's individual level, then usually it requires fewer sample to give you enough power. But if you are doing randomization on the school level, so each school in your experiment counts as one data point. So that means you have to find more schools to meet the enough power. I know it sounds like very complicated, and you wonder, how am I ever gonna figure out how much power I have and how big the sample size I need for my experiment. Actually, the power calculation is really easy because of the the software we have. So there are two ways to calculate power. The first one is called optimal design software, which is kind of really straightforward. You just plug in the structure of your sample, like whether it's clustered or the significant level, effect size, standard deviation, whatever you use to measure your effect size. And then the beauty of this software is we'll draw a graph showing like this. So it's it will give you a graph. So as your cursor moves along the graph, and it gives you like the power. So for example, if we stop here, then it will tell you with the effect size of 0.02 standard deviation with sample size 190 students or clusters, then you get only 0.3 power. But if you have a bigger effect size, then for example, from 0.2 move to 0.4, then your power will be efficient. So this is, the OD software gives you a more kind of visualized result. Alternatively, you can also use Stata, and the two command to calculate power here is either power. You can just help power in the Stata software. It's very straightforward. It gives you the power and sample size. And also, if you want to do a cluster randomized control trial, then you can use this command, cluster sample size. Which is very straightforward. It's the same command you use to run regression. So I'm sure you guys can figure that out easily. So this is the second part of today's session. Now let's move on to the third topic we're going to cover today, which is the threats. Ideally, we design a randomized control trial, and we covered the sample size, make sure we have enough power, and we do the randomized assignment, and everything will be work perfectly, right? But the fact, is when you implement your experiment, it's, a lot of things may come up. So, things that, cannot kind of make our experiment run perfectly, then becomes the threats to the internal or external validity. So remember, the whole idea behind the experiment method is we want to maintain counterfactual in the control group. But when, in the real world, there are many ways that your control group can be contaminated, either by differential attrition, spillovers, or imperfect compliance. So the first one we're gonna take a look at is attrition. What this means is individuals that your sample that were in the baseline, but then by the end of your experiment, when you're trying to follow up at the end line, they disappear, right? There are many reasons why they can disappear, right? It could be, students or units dropped out of the program. Or sometimes, the outcome variable, they don't want to give you that information. So they're denied information. And also, sometimes it's really, hard to predict or control. Like, students may drop out of school because illness or even death. So this kind of, sources of attrition can have impact on our experiment. So if the attrition is just random, right? Some students will, leave the experiment, then it's probably not a big problem. But sometimes attrition could be a threat to our experiment, because when we design the experiment, we want the randomization, the two group, control and treatment group, achieve a balanced level, meaning the only difference is, one get treatment and the other don't. But say, for example, in our eyeglasses experiment, if, let's say, students have some, preference on eyeglasses, let's say, for example, girls, they, choose not to wear glasses. They choose not to participate in the program because girls may kind of, think it makes them dizzy, eyeglasses make them dizzy, or they don't like, the appearance of wearing glasses. So then that will be, cause this kind of non-random attrition will lead to imbalance of our sample. So then, if that happens, then all we have at the end of the experiment will be all boys, right? So that will be a threat to our experiment. But that's not the end of the world. There are ways that we can deal with attrition. The first kind of, intuition is when attrition happens, say, girls choose not to participate in the program, then we can devote resources to track the participations. We can try to, from the designing phase, and trying to minimize the attrition. But if that doesn't work, if there's still attrition, then we want to check whether or not after the attrition, the two groups are still balanced. So the first step, generally, we wanted to report the balance after attrition and examine whether it's a differential attrition. So this is an example from a paper that I published before. So there are some attrition in this experiment. So what we need to do basically just to use our data to prove either the attrited students are after attrition will be the same or not, even if it's there is. So for example here, we can see that mom's education is significantly correlated with students attrited from the treatment group, which is fine. You just need to put everything on the table and explain and discuss how does that affect your the impact you measured. So ideally, if it's balanced after attrition, then it's not a big threat to the experiment. But sometimes when it's even if it's not balanced, which is also fine, you just need to think carefully about how that's gonna affect your result. That's all. And so the table I show here is a traditional way to, same as our kind of balance test for randomization. You look at each variable and then see whether the two groups are still balanced or not on each characteristics. But you can also do kind of other kind of methods. So more recently, there's this bounce estimators. So basically what this means is you acknowledge that some portion of your sample dropped out from your experiment, but you can still kind of estimate the impact, kind of the boundary of the impact, get a lower and upper bound of your impact. So the intuition behind the bounce estimator is basically to trim either the sample in the control group or treatment group, so that you basically manually make the two groups both have some attrition, right? So it's still like the attrition happened in the control group, which will be the same in the attrition happened in the treatment group. So after you either get rid of the top ones in your sample or the bottom ones, and you just use the remaining sample to estimate the boundary. So the Lee bounds, which was kind of invented by Lee in 2009. So gives you an estimate of a confidence interval. So the two assumptions for use this kind of bounce estimation is one, your assignment is random, and also the direction of attrition only happens in one direction. So then you can just run the same kind of same as regression, right? You measure the impact, but instead of using the regression method, you use Lee bounds as the command in Stata, which is also very straightforward. So Stata actually will do most of the calculation for you. The second strat to internal validity is spillovers. So what does this mean? Spillovers usually means, the behavior in the control group may be influenced by, by your experiment, basically. And so this could dilute the impact you measure. So for example, either information campaign or back to our example, eyeglasses. So when you give, say, this goes back to, remember we talked about the question. why do we need to think carefully about at what level you want to do the randomization, right? If you do the randomization at individual level, say students in the same class, some students got their eyeglasses or information campaign, and some students in the same class, they don't get anything, right? So this could be a problem because the students who got their glasses sitting in the same classroom, right? Then the students in your control group will go back home and ask their parents to get a pair of glasses for them too. So then you have this kind of, spillover, right? So you don't have a pure control group. So the information or your intervention could easily spread to the control group. So this could be a problem. So that's why when we design the experiment, we have to think carefully about the unit of randomization. So usually, say if we expect that the spillover will happen within school, then we can move on to a higher level, do the randomization. So for example, the eyeglasses example, instead of run the randomization at individual level, we can do it at school level. So the assumption behind this is students from school A have very limited interaction with students from school B. So in this way, we can kind of control the spillover effect. The third threat to internal validity is called imperfect compliance or crossovers. So the example could be that if students kind of, basically they don't listen, right? They're not the perfect complier to your randomized controlled assignment. So for example, the eyeglasses program. If in a rural village, students from school A are all getting glasses because they're in a treatment school, and then the parents from the same village will try to, in theory, they can move their students from school B to school A in order to get the free glasses, right? So that could be a potential problem, or even let's say no parents move their students around. Even the assignment is perfect. We did everything right. We're in a perfect design. It still could be risk of imperfect compliance. Why? Because say you assigned treatment school, right? So when you give free eyeglasses to students, all the students in the treatment group, what's going to happen is the students in your treatment group, some students will listen. They get their free eyeglasses and they will wear their glasses. So that's perfect for our experiment, right? Because we wanted to compare the myopic, the nearsighted students who get eyeglasses, wear them, with the students in the control group, right? They are myopic, but they don't have eyeglasses. So what we want to compare ideally is A and the C here, the compliers. But the real world is not perfect, because when you give eyeglasses to the students in the treatment group, some students will choose not to wear them because they're afraid they'll be teased by their peers, or they have some concern about wearing glasses. So these kind of students, when they're in the treatment group, when they receive the treatment but they're not uptaking the treatment, we call them no-shows. And the same thing could happen for the students in the control group, right? In our perfect experiment design, we don't want them, at least for the implementation period, we don't want the students in control group wear glasses, but we cannot really prevent students to get eyeglasses on their own, right? So these group D students here, we call them crossovers. So this is example of the imperfect compliance, which is not ideal for us to measure the true impact of eyeglasses, because within each group there is some like mixed result, right? So in the treatment group, you have students supposed to wear glasses, but they're not wearing. And in a control group, you want to see students all not wearing glasses, but some students are getting eyeglasses on their own. So there are some imperfect compliance, right, to in our experiment. So this introduced the concept called intention to treat, the ITT. So what does this mean is intention to treat. This measures what happens to the average child who is in the treated school in this population. So we don't really care about students who actually wearing glasses in the treatment group, and we don't even care about the students who in the control group got the eyeglasses on their own. So we just compare the average treatment and the control group. It's still a causal effect because we're still comparing two identical populations. But I want you to think about this is a causal effect of what, right? It's not the true measure of wearing glasses, right? So what we're measuring is just providing free eyeglasses versus not providing free glasses, right? The average of the two groups, instead of looking closely at who actually wearing the glasses and who do not. So this is clearly not a measure of the impact of eyeglasses, but it is a useful measure because it measures the overall impact of the intervention, which is important. Because when you run this experiment, or you carry out this policy, say give all students glasses, some students may choose not to wear them. So in a kind of policy relevant point of view, ITT is actually measuring the actual impact, the overall impact of the intervention. And then again, with the imperfect compliance, we also want to know what's the impact of the students who actually received, the students who actually wear eyeglasses. Is it possible to measure this? The answer is yes, but it's a little bit trickier than just compare the average between the treatment and the control group. So the treatment on the treated, the TOT, impact is also, sometimes it's called local average treatment effect, LATE. It's the same concept. So how do we do this? So if there's imperfect compliance, then the comparison between the two groups is smaller, right? Because some students in your treatment group are not doing, what they're supposed to do, which is wearing glasses. So the glasses for this kind of students are being kind of wasted. So that kind of dilutes the impact you can get. So the treatment on the treated parameter actually corrects this imperfect compliance and scaling it up by kind of this take-up difference. So again, if we write the equation out, so the treatment on the treated, the TOT is actually the average effect between the two groups, which is ITT, and divided by the difference in the probability of actually being treated in a treatment group and in a control group. Again, this estimator is also called a WALD, the treatment on the treated, i.e. the impact from the compliers is basically the ITT, the mean in the treatment group minus the mean in the control group and divided by the probability difference in the take-up rate in the two groups. So here I make it more kind of intuitive. So let's say first we figure out the intention to treat, right? So let's see the outcome test score here. If we ignore the gray area, which is, students who actually wear glasses or not, let's just, forget about the gray now. We just look at the outcome on average for the treatment group who, we provide glasses. So say their test score in the end line is 95. And for the students who are in a control group who did not get eyeglasses, their test score at the end line is 82. So the ITT, which is just compare the 95 from the treatment group with the 82, the average from the control group. So we know it's 13, right? So how do we get the, the treatment on the treated, the TOT, is we also figure out, the probability of uptake rate. So basically is the percentage of the students who actually got the treatment. So in the treatment group, because we give glasses to everyone, the uptake is higher, say 70%. And for this control group, the students who actually got eyeglasses on their own is only 10%. So we take account of the difference in the probability of the uptake rate. So divided by the ITT divided the probability. So the actual treatment impact on the treated. So for the students who got their glasses and actually wear them, compared to the students who completely don't have eyeglasses at all, the impact is much larger. So so we see the TOT here is 22 compared to ITT is only 13. So when we trying to figure out the true impact in the perfect kind of compliance situation, the TOT is the treatment on the treated is much larger than the average treatment effect. So why do we care about ITT and TOT? Why not just always use TOT? Because that's the pure, true impact of students who got eyeglasses and wears them. Well, like I said, the intention treatment effect is more policy relevant because we may not be interested in the medical effect of students wearing glasses, but what we care about as a policymaker is what would happen under a actual eyeglasses program. Say I'm a policymaker, I carry out this policy, give glasses to all students, and some students they choose not to wear, which is normal and which we measured in our experiment. So the ITT, even if the impact is smaller, but that's kind of resembles the true impact from the real world. And also TOT can also provide valuable information for decision making because the TOT gives the effect of the intervention on the ones who comply with the program, the true impact. If we kind of want to really do a, say, cost effectiveness analysis to figure out, many kind of, to compare many educational interventions, which one will have the biggest impact if it's implemented in a perfect way, then this the TOT will give us a more kind of precise and accurate estimate of the impact. So both ITT and TOT have their kind of, pros and cons, and it's useful to report both of them, especially when you have an imperfect compliance in your experiment. So the three internal threats to validity we just covered. And the last part of today's session, I'm going to briefly talk about the external validity threats. So usually we consider two kind of threats. One is the behavioral response to evaluation. This will raise a external validity threat. So I'm going to explain why. Even, when we design the evaluation, the experiment in a perfect way, say, everything from the designing phase is perfect, but you cannot really prevent the kind of your sample to change their behavior. So the two typical behavioral responses to evaluation, one is called John Henry effect, which refers the members in the control group work harder to compete with their peers in the treatment because they are unhappy about having been assigned to the treatment, to the control group. So a fun story about behind this John Henry is he was a worker in the American Railway in the 1870s. And the researchers were trying to do an experiment to see whether or not using machine to build railway will be more efficient than use railway workers. So because John Henry knows that this experiment is going on, so he works harder because he knows that, he's in this experiment and he's not happy about having been assigned to the treatment group. So he wants to change his behavior and work harder than the machine. So, he works harder to outperform the machine and eventually died from working so hard. So the John Henry sad story resembles, which is a common kind of behavioral effects under the experiment. Usually people, when they know, especially when you assign student or, when they know they're in a treatment or in a control group, especially when your sample know that they're in a control group, they may change their behaviors to compete with their peers who are in a treatment group. So this is called John Henry effects. So another kind of behavioral response is called Hawthorne effect, which is, this refers to when they know that no matter it's in a treatment or control group, when people know they're in the experiment, they will change their behavior. So the story behind this is also worker in the factory, electric factory. So the researchers trying to kind of doing different experiments to increase the workers' productivity. Because the workers know that they're being experimented, so they work harder during the experimenting phase. So the researchers saw a huge gain in productivity during the experiment phase. But once the experiment stops, the gains disappear. So this could be an external stress to our experiment, because once, say students know that they're being tested in the experiment, so they may, work harder, or they, take the exam more seriously. So when this kind of, behavioral response happens, what we measure is not the true effect of the experiment. So how, what can we do to limit this kind of evaluation-driven effects? One kind of, classic way to deal with this is, again, use a different level of randomization. So there's no kind of information spillover or crossover. And also we can also do the minimize the silence of the evaluation as much as possible, right? So we do not announce everyone, hey, we're doing the experiment. We don't do any kind of announcement on the experiment. And also we wanted to make sure our research, especially the field team, is informed that, they should not reveal any kind of treatment or control information to our sample. We can do blind data collection. So even the field, maybe data collection team don't know which school is, being in a treatment group and which school are in the control group. And the third way to deal with this is we can also measure the kind of evaluation-driven effects in a subset of the sample. So if we know that, some students in certain school are trying harder because they know they're in the control group, then we can kind of take notes on that and then either tease out this subset or, do some other kind of way to control the influence of this kind of behavioral response. The other kind of threats or kind of concern on the external validity is called generalizability. So which this means is like how much your result can apply to other contexts. Say we run this eyeglasses experiment in rural China. Will that work in other countries, right? Once the kind of program is generalized to other population, will we see the same impact? And also we need to think about the sample representative of our population. Even we say we run our experiment in rural China, does that mean we covered the entire rural population in China, or we just kind of randomly selected some sample size to run the experiment? And also how sensitive the impact to the changes, right? So for example, if we do a scholarship program, the experiment, the treatment we measured is, say, the scholar kind of incentive is, say, $2,000. And then we see this huge impact. But what if we decrease the scholarship amount from $2,000 to, say, $1,500? Well, these kind of small changes will significantly change the result. That refers to the sensibility of the program design. So to kind of conclude all we covered in today's session, which is a lot. So yes, the RCT is a very good way to figure out the causal impact of certain intervention, which is golden standard of doing research. But there are also many threats that we have to keep in mind. Basically, always keeping your working memory, either in the designing phase, data collection, implementation, and also later on when you analyzing the data, always you need to keep in mind the internal and external validity of randomized evaluations. So that means RCT is not one solution to all the problems we're facing, but it's pretty good as far as a kind of research methods goes, as long as we keep in mind this kind of the 3 internal validity threats and the 2 external validity threats, and that will kind of give us a more precise and more scientific and rigorous result of our experiment. Also, this is just a summary of what we covered today. The design phase, we need to keep in mind about the power calculation, which is super important. Without efficient power, we're basically, either you're overpowered, meaning you're wasting a lot of resource, either in budget or human power to run the experiment, or if you are underpowered, that means, we can face type 2 error, after the whole kind of evaluation that we figure out the power is not enough, meaning we can't, draw a confident conclusion from the whole kind of experiment. So the designing phase, we need to keep in mind about the, the power and theory of change, but also in the implementation phase, we also need to think about the challenges we are going to face. We need to kind of devote resources to prevent attrition, spillovers, and partial or imperfect compliance. And also for the external validity tracks, we need to be aware of the experimental effects and also take caution when we generalizing our impact to other part of the population. So that's today's kind of session. If you're interested, I recommend you take a look at these further kind of study resources. The first one is Professor Roselle's new book about invisible China, which is a kind of nice read, summarize the randomized control trial that our research center have been doing in the past 10 years, and also summarize the the problem, the social inequality problems in rural China. And the second book I recommend is Mostly Harmless Econometrics, which is a really nice book. I keep it handy. Still, many times I'll refer to this book. It gives you a lot of examples of experiments and also explain the kind of econometrics behind the theory. And also the last one is from J. Paul, using randomization in development economics research. So which also summarize a lot of experiments that J. Paul ran, mostly outside of China. So if you're interested, you can take a look at these 3 books. And also you can check out our website that we have a lot of research projects going on, and also all the examples Scott Roselle covered in his session and today's session. We have lots of publications based on the field experiment we run. So that's also a good kind of source for you to continue this topic.
So Huan, there's a question. Thank you. There's a question in the question box about by Rohan Ray. Can you see it there? How often do you get to see the actual uptake as a researcher? You do know the treatment assignment, but actual uptake rates might not always be observed. Then what do you do?
This is a very good question. Yes. So Rohan, can I ask you to kind of provide a little bit more detail about what kind of experiment in your mind that can be hard to measure the uptake?
Right. So what I'm thinking is that in this particular context with the glasses thing, right, you can kind of monitor if they're wearing it or not, like when they come to school. But let's see, if I see the impact of mosquito bed nets on malarial prevalence, right, then you wouldn't know exactly if the household is kind of using the bed nets when they go to sleep at night, right? So then can you calculate the LAT or the TOT estimates in such a case where you don't exactly know for sure if the bed nets are being used? You can probably ask them at the end line survey, did you use it? But then that could also be kind of a biased response if it's self-reported. right? So how would you kind of tackle in such a situation? Like, what's the way to go?
That's a wonderful question, and I'm glad you're thinking about the reality. Even thank you for your question. Even for I think for the eyeglasses intervention or the mosquito nest in your example, it's the same idea. When we go out and do the survey and ask students, are you wearing your eyeglasses, or ask the villagers, are you using the mosquito nest we provided? The answer most of the time, self-reported data, they will say, yes, of course, I'm wearing it.
But that's not true. That's not true. Sometimes they'll exaggerate. Okay.
Yeah.
Oftentimes they'll tell you the truth, but sometimes they will. So you have to be careful about that. So I wouldn't say, I'd say most of the time sometimes they'll try to make you happy, but other times that they'll actually tell you the truth. So how do you go about it, Huan?
Yes. So in order to prevent, get the real data from the uptake, in our eyeglasses program, we actually send out this kind of unannounced team, just random check in school, and actually go to the classroom. And so we have a list of students who supposed to wear their glasses. So we kind of count the students who in the class are wearing glasses when they're in the classroom. And so that's like a way to verify. It's not like we don't trust their self-reported data at all, but that's a way to kind of get the precise and more reliable measure. And the same, for the mosquito nest experiment, you're
going to have to go at night. You're going to have to send a team at night, and maybe you don't go to every single village, right? Maybe you can pick a subsample and then see, are the self-reported ones correct or not, right? Or how much bias there is. And but of course, we call them guerrilla visits to look if they're wearing that. The other problem is, though, what happens if you come to a singing class, right? They happen to be in art class and they don't need their glasses. Maybe you undercount, right? And so what we decided in the third time, we said, we're going to call out the kids and say, bring your glasses up to us and show us that you at least have them at school. So there's a lot of that you have to worry about it, and it's not easy. Great question.
Thank you so much. Thank you.
Looks like you've done this before, Rohan.
I actually work on RCTs. Yes, that's right. Yeah.
Fabulous. Yeah. But the key is you better figure. So we did a study where we gave 6 months worth of anemia powder for babies, right? And how do you know how many they took, right? And so we put these great big pouches on their wall and asked them to drop the empty package in each one of them. And you hope that they didn't pour it out and cheat, right? And you have to worry about that. And of course, if you may not find any impact on IQ, but maybe you should find an impact on HB level, right? So yeah, it's not easy. It's a very important question to figure out.
Thank you so much. Thank you.
Other questions? Chen, do you have a question or not?
Yes. Thanks, Huan, for the lecture. I think it's very important for us to comprehend this basic knowledge. I also have one question regarding the power calculation. So I want to know, how do you usually choose an appropriate value of the expected size or the expected treatment effect while you are calculating the power? Because sometimes I found in the literatures, like they have various values that the previous studies have conducted, but I just want to know, like, how do you choose it?
Yes, we also look at, the experiment has been done, in some other countries or some, similar interventions, and we're trying to make like a reasonable, basically guess on the kind of effect size when we design the experiment. Because in the designing phase, you don't know that, how big the true impact would be. So one is from the, reading the literature and trying to figure out what's the best guess. And the second kind of way to think about this is you also want to make sure the effect size has some kind of meaning in reality, right? So for example, in some other studies, we know that they have done many experiments and only increased the student test score by 0.0001 standard deviation, which is significant, but it doesn't have really kind of practical meanings. So another way to think about this is we set like a effect size and then backwards calculate power and see how big a sample size we need.
All right.
So you get an effect size that if you go and report to the Bureau of Education or the Department of Education, say, hey, we reduced class size by 10 students and we increased test scores by 5 points, right? Now 5 points may be 0.3 standard deviations. Can you tell those guys in the Department of Education how big that? And then you might say, well, wait a minute, with the testing we used, we know that 0.3 standard deviations it's like a half a year of learning. So we can increase by a half a year of learning by reducing sample size. And if it's not that big, we don't want to do it. So you think like that, like what would be, is exactly what Wang said, what would be a meaningful effect size? And if it's smaller than that, the leaders wouldn't be interested, right? So I want to figure out if it'll make that big of an effect size. And if it's not going to make that big of an effect size, no one's going to be interested. So you have to do both of those things. What happens in reality versus what the demands on you would be, and look at it.
Okay, thank you very much.
Hi, I have a question too. I know you will make some balance check before the experiment. However, there are unlimited characteristics of individual, and you just choose some of the control variables. So what if some variables, then after the random sample, which is not balanced in the treated group and untreated group, and do you think it will cause some endogenous problem to your topic, or do you think because of randomization we don't care about them?
Again, very good question. So remember, we mentioned the theory of change. So when you design a program, you want to think through the causal chain, right? What might change from your input all the way to your goal, which is the kind of, whatever test score or, health level you're measuring. So in between, there are some, say, for example, students, confident in school, or some, other measures that you think through the causal chain, the theory of change. So when you design the experiment, you want to capture as many kind of possible channels throughout the experiment as possible. So in this case, at the baseline survey, we have to think through the entire process and trying to capture as many variables as possible. So basically, we want to try to measure everything that can be measured. Also, you have to kind of balance between the amount of questions you ask students and what are the really kind of key variables that could affect students' outcome. So in this case, there might be some variables that we're missing, like how much student like school, right? This kind of very subjective measure. Maybe we cannot really, capture that data, but, how much does that affect the student's outcome, which, could be small, right? Depending, what kind of assumption you have. So one, definitely we wanted to collect data on the key variables and trying to make sure these variables are balanced. And two, there is a trade-off. Sometimes, yes, we cannot get data on everything. So it's possible there are some kind of chain that are missing. So that's why we need to kind of really be careful when we design the experiment.
Okay, I see. I have another question. I wonder in general, the RCT, do we more focus on the exact point estimates, or do we more focus on the directions of the direction of the relationship between the program to the outcome of the individual?
I would say both, because the point estimate gives you a precise impact. That's the whole point of running RCT, is we can measure the causal impact. If you do this and then you got this much impact. So that's important. But sometimes, because there's something, sometimes the intervention is not always working, right? So we don't see the significant impact of certain interventions. In this case, yes, there's no significant impact, but there's direction. It's still kind of moving students kind of towards the right direction. That's something we can learn from the experiment too. So
okay. Because I am thinking about the contents about crossover and no-shows in your lecture. I think if we just focus on the direction, both of these populations in the treated group and untreated group will not cause negative effect to our goal, because we could still get the right direction of the estimate, and also the estimate will be underscored in the regression.
I think you can write, you're a good policy brief writer.
Yeah, but I think
you measure the impact.
Right, but I think that you want to be able to measure the spillover, and you want to measure the precision of the implementation, right? I mean, and is it something that you did wrong, or is it something that's going to happen when you go into a real field? There's also two types of implementations. Okay, there's efficacy trials. Okay, and efficacy trials are, I'm going to do absolutely everything I can to make this intervention work. I'm not going to let anybody cheat, right? So for the vitamins, you saw the efficacy trial was the teacher poured water, gave the kid the vitamin, and then watched the kid swallow it, right? Now, we knew every kid took that vitamin. So there was no attrition on the treatment. The treatment was 100%. There was no LATE estimate. It was all ITT. Okay, ITT and LAT is the same. But then we went out and said, okay, let's just go let teachers do this as if the Jiaoyuzhu, as if the Bureau of Education was going to implement this. And guess what? Oh my God, some teachers didn't do it. They said, I don't want to give my kids medicine, right? I mean, we said vitamins isn't medicine, but some teachers didn't. Others time, kids put the vitamins in their mouth. And then when the teacher walked to the next one, they took it out and threw it out the window, right? And so, but we learned a lot there, right? Because we then saw the ITT fall, and the Bureau of Education cares about that ITT because they're going to say, we're going to spend this much money do we like this big of an impact, right? The efficacious trial was this much. We could get this much, but we're only getting this much. Is it worth it? So those are the kinds of things that you really have to worry about. So.
Okay, I see. Thank you.
Bye, everyone.
Thank you.
Bye.
Bye.